The real part is 4 by 25 and imaginary part is minus 3 by 25. That's it. If you do this much, you will get 3 marks. That's it. 0 is a rational number since 0 can also be written as 0 by 1. All rational numbers when expressed in decimal form are either terminating decimals or recurring decimals. The square root of a positive integer which is a perfect square is a rational number. Hello dear students, welcome to this session of basic mathematics class. I am Mr. Niranjan, faculty department of mathematics, Vidhyaashram PU College, the temple of excellence. In my previous class, we have discussed regarding the addition, subtraction, multiplication, division of a complex number. So in this session, I will take one problem on complex number, then I will go to rational and irrational numbers, right? Now let us come to the first problem. Reduce the given complex number in the form a plus ib. This is very important problem. Now, just what is the problem given? 1 by 4 plus 3i. Write its real part and imaginary part. So we have to reduce this into the form a plus ib, then find the real and imaginary part. So what is the complex number given? Given equation, let us call z is equal to 1 over 4 plus 3i. Now to convert this into a plus ib form, rationalize this. 1 over 4 plus 3i, just multiply both numerator and denominator by 4 minus 3i. Just multiply and divide by 4 minus 3i by 4 minus 3i. Multiply this. 1 into 4 minus 3i is 4 minus 3i divided by, this is 4 4s are 16, that is 4 square is 16, minus into plus it is minus, 3 3s are 9, I into I is I square. Since you know I is equal to root of minus 1, I square is equal to minus 1. This can be written as, so 4 minus 3i divided by 16, I square is minus, minus into minus plus. So 4 minus 3i divided by 25. Now this can also be written as 4 divided by 25 minus 3 divided by 25 into I. So this is of the form a plus ib. Right. Now what is to write? Write its real part and imaginary part. So the real part of this complex number is 4 by 25 and the imaginary part of this complex number is minus 3 by 25. That's it. So the real part is 4 by 25 and imaginary part is minus 3 by 25. That's it. If you do this much, you will get 3 marks. That's it. Very simple problem. Okay. Now let us come to the next very important concept, that is rational numbers. First let me discuss rational number, then irrational numbers. Now any number of the form p by q, a number in the simplest form p by q where p and q are integers and q is not equal to 0 is called a rational number. Any numbers of the form p by q where q denominator is not equal to 0 is called a rational number. The set of rational numbers is denoted as q. For example, 4 by 7, 3 by 5, minus 2 by 3. These are all examples for rational numbers. Any numbers of the form p by q is called a rational number. So that is, the set of rational numbers is denoted as q is equal to p divided by q such that p and q belongs to any integer and q is not equal to 0. A number of the form p by q is called a rational number and denoted as q. Now, where the value of q is not equal to 0. Every integer is a rational number. Every integer can be expressed in the form of p by q. 0 is a rational number since 0 can also be written as 0 by 1. So, is of the form p by q where p and q are integers and q is not equal to 0. Next, the square root of a positive integer which is a perfect square is a rational number. So for example, if a square root which is a perfect square, v is also an example for a rational number. That is, square root of 16 is 4. 4 can also be written as 4 by 1 which is of the form p by q. So square root of 16 is 4. This 4 can also be written as 4 by 1, that is of the form p by q. Similarly, square root of 25, that's equal to 5. This can also be written as 25 can be written as 5 by 1. Again, this is of the form p by q. So therefore, The square root of a positive integer which is a perfect square is also an example for a rational number. Now you got an idea what is a rational number. Now let us come to some properties. Rational number in the lowest term. Now a rational number of the form p by q where q is not equal to 0 is said to be the lowest form if the integers p and q have no other common factors other than 1. That is, if p and q are co-prime or HCF of p and q is 1. If the numbers are co-prime, if they don't have the common factor, if they don't have the factors other than 1, then such rational numbers of the form p by q are called as the rational number in the lowest form. That is, if the HCF or the S common factor or the GCD is equal to 1. That is co-prime, relatively prime numbers. For example, 7 by 14 is a rational number but not in the lowest form. If 7 by 4 can be expressed in the form 1 by 2, then it is called a rational number in the lowest form because the GCD of 1 and 2, highest common factor of 1 and 2 is 1. All rational numbers when expressed in decimal form are either terminating decimals or recurring decimals. So, any rational numbers which is expressed in the decimal form are either terminating decimals or recurring decimal. Let me explain what is the meaning of terminating and recurring decimals. Now, let us come to an example. 1 by 4. 1 by 4, if you divide 1 by 4, 10, that is 0.25. If you put a point take a 0, 10 by 4 is nothing but 0.25, which is a terminating decimal. That means 1 by 4 is exactly equal to 0.25. It stops here itself. So, therefore, this is called as the terminating decimal. Whereas 2 by 5, if you divide 2 by 5, so 20 divided by 5, that is 0.4. 5 4s are 20. This is also a terminating decimal. So 0.4 is the exact value of 2 by 5 and 0.25 is the exact value of 1 divided by 4. So therefore, these two are examples for a terminating decimal. It will terminate. Now, whereas 1 by 3, if you divide 1 by 3, 0.3333, you will get 333 up to infinite terms. So is a non-terminating decimal. 0.333 etc. This is an example for a non-terminating. It won't stop. It will repeat 333. Similarly, 1 by 7. If you divide 1 by 7, you will get 0.142857. Again 142857. Again 12857. So it will repeat. Therefore, this is also an example for a non-terminating recurring decimals. So these are the examples for terminating and non-terminating recurring decimals. Now, let us come to the next type of problem. Example, express each of the following rational numbers as decimals. Now, for example, 3 by 4. 3 by 4 can be as 0.75. Now, 15 by 8. 15, if you divide 15 by 8, you will get 1.875. Similarly, 8 by 25. 125. 8 by 125 can be written as 8 into this 125. Just for 125, multiply and divide by 2 cube. So, multiply and divide by 2 cube means multiply and divide by 8. 2 to the 4, 4 to the 8. So, these two gets cancelled. This is equal to 8 into 2 cube is 8 divided by 125 into 8. This can be done 8 8s are 64 divided by 1000. 64 divided by 1000 can be written as 0.064. So, that is nothing but a rational number in the form of decimals, right. So, 3 by 4 is 0.75, 15 by 8 is 1.875 and 8 by 123 can also be written as 0.064. Now let us come to the next concept, recurring decimals. Recurring decimals. In recurring decimal, a decimal representation in which all the digits after a certain stage are repeated is called a recurring decimal. So, just I have given the example for recurring decimal. At a certain stage, if all the digits will repeat it, then it is called recurring decimal. Say for example, 1 by 3. 1 by 3, if you divide 1 divided by 3, you will get 0.333. So, therefore, this is 0.3 bar. this is an example for a recurring decimal. That means a decimal representation in which all the digits after a certain stage repeats. It goes on, repeats. Here 3 repeats. So therefore 0.333, that is nothing but 0.3 bar, which is an example for the recurring decimal. Now, what is a mixed recurring decimal? Mixed decimal recurring means a decimal in which some digits after the decimal point is not repeated. Some of the values will not be repeated. That means a decimal in which some digits after the decimal point. Mixed recurring decimal means a decimal in which some digits after the decimal point is not repeated, and then some digits are repeated is called as the mixed recurring decimals. So, a decimal in which some digits after the decimal point is not repeated and then some digits are repeated is called the mixed recurring decimal. If they are repeated, then they are called as the mixed recurring decimals. Here example 6.12555, this is an example for a recurring decimal. Now let us take, suppose if let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 to the power of n into 5 to the power of n, then the decimal expansion p by q terminates. This will terminate. So, this is very important formula. 2 to the power of n into 5 to the power of m is used to find whether the given problem is, if let x is equal to p by q be a rational number such that the prime factorization of q, the denominator, is of the form 2 to the power of n into 5 to the power of m, then the decimal expansion p by q is called the terminating decimal. This is called the terminates. It terminates. So, if the denominator is of the form 2 to the power of n into 5 to the power of n, then the decimal p by q, there is a terminating decimal. Now, if p by q is a rational number such that the prime factorization of q is not of the form 2 to the power of n into 5 to the power of m, then the decimal expansion p by q is called a non-terminating decimal. Now, let us take an example. Without performing the long division, state whether the following rational number will have the terminating decimal expansion or non-terminating decimal expansion. So, let us convert the denominator into the form 2 to the power of n into 5 to the power of m. 17 by 3125 can also be expressed in prime factorization. Let us express the denominator 3125 as 5 to the power of 5. So, 3125 can also be written as 5 to the power of 5. 5 into 5 into 5, if you multiply, you will get 3125. So, this is of the form 2 raised to 0 into 5 to the power of 5 is of the form 2 raised to n into 5 raised to m. So, therefore, this 7 by 325, 3125, 3125 is a rational number having a decimal expansion. This is an example. This is 17 by 3125 is a rational number having decimal expansion. Now, because the denominator 3125 is of the form 2 to the power of n into 5 to the power of m. Now, let us take one more example, 13 by 8. So, this 8 can be written as 2 cube. So, this is nothing but 13 divided by 2 cube. So, 2 cube into 1, this can also be written as 2 to the power of n. So, therefore, this denominator can be written as 13 divided by 2 cube into 1. So, we can also write this as 5 to the power of 0 because 5 raised to 0 is equal to 1. So, the denominator is of the form, this is of the form 2 raised to n into 5 raised to m, 2 to the power of n into 5 to the power of m, right. So, therefore, this is also an example for a decimal expansion, 13 by 8. So, this 13 by 8 is having a decimal expansion. Let us take one more example, third one, 64 divided by 343. Now, 343 can be written as 7 cubes, 7 into 7 into 7, 7 sevens are 49, 49 into 7, 343. Now, if you observe carefully, this is not of the form, this is not in the form of 2 raised to n into 5 to the power of m. So, this 7 to the power of 3 is not in the form 2 raised to n into 5 raised to m. Therefore, That's decimal 64 by 343 is not a terminating decimal. Terminating decimal. This is not a terminating decimal. This is how we are going to. So, if the denominator is of the form 2 to the power of n into 5 to the power of n, then the decimal, then the fraction, then the given problem is a terminating. If not, then it is called a non-terminating decimal. Okay. Now, let us come to the next concept, very important, irrational numbers. A numbers which cannot be in the form p by q, any number, a number which cannot be put in the form p by q, where p and q are integers and q is not equal to 0, is called an irrational numbers. Numbers which are not in the form p by q are called as irrational number. For example, root 2, root 3, root 5, root 7, these are all example for a irrational number. So, root of 7. So, this cannot be put in the form of this is not in the form of p by q. Therefore, this is an example for a irrational number. So, irrational numbers means numbers which are not in the form p by q. Now, let us come to a very important problem. In the examination, you may expect this question for 3 marks in this irrational. Very important problem. Prove that root 2 is an irrational number. So, we have to verify this by the method of a contradiction. Now, let us assume that we shall prove this by the method of a contradiction. Let, if possible, let root 2 be a rational number. Let us assume root 2 as a rational number. That is, let root 2 is equal to p by q, where p and q are integers and q is not equal to 0. Now, then let p and q are co-primes, that is, the highest common factor of p and q is not equal to 1. So, that is, root 2 is equal to p by q, or cross multiply it. If you cross multiply, root 2 into q is equal to p. Squaring on both sides, if you square, root 2 whole square is 2, p square is 2 into q square is equal to p square. So, let p by q is equal to root 2, cross multiply it, root 2 into q is equal to p, squaring on both sides, square root gets cancelled, 2q square is equal to p square. That means, this 2 divides p square, 2 divides p square, which implies 2 divides p also. That means, the value 2 will divide p square, which implies 2 also divides p. If 2 divides p means definitely p is an even number. See, listen, let us assume that, let us prove by the method of contradiction. Let us assume that root 2 is a rational number. So, what we have to do here means, let us assume the given number root 2 is a rational number, and we have to verify that the given assumption is wrong. It is not a rational number, it is an irrational number. For that, let us assume root 2 as a rational number. Rational number is of the form p by q. That means, let root 2 is equal to p by q, where p and q are integers and q is not equal to 0. Now, let root 2 is equal to p by q, cross multiply, root 2 into q is equal to p, squaring on both sides, square root gets cancelled, 2q square is equal to p square. 2q square is equal to p square means this 2 will divide p square. So, if 2 divides p square, if 2 divides any number means, then it is nothing but an even number. 2 divides p square implies 2 also divides p, therefore, p is an even number. Now, on the other hand, let us consider this p is equal to, let p is equal to 2k for some integer k. So, where k is an integer, and we know that p square is equal to 4k square. Square it, p square is equal to 4k square. Now, since we know that what is p square is also equal to 2q square. Substitute here p square, since p square value is equal to 2q square. Let us consider p is equal to 2k. So, where k is an integer, some integer, square this. Squaring on both sides, p square is equal to 2 square is 4k square. Since we know the value of p square is equal to 2q square. Substitute here, 2q square is equal to 4k square, divide by 2, q square is equal to 2k square. That means what? Q square is again an even number. If q square is even number means q is also an even number. So, here in the first case p is even number, in the second case q is an even number. That means, now p is in even and q is even, which implies p and q have a common factor 2. So, if p is an even number and q is an even number means definitely p and q will have the common factor as to 2 is the common factor, which contradicts our assumption that P and Q are co-primes. So, which contradicts the fact that P and Q are a co-prime. Hence, our assumption that root 2 is rational is wrong. Hence, root 2 is an irrational number. That's it. See here, very simple. P and Q will have the same common factor, that is 2. So, if 2 is the common factor, means which contradicts our fact that P and Q are co-primes. That means our assumption root 2 is wrong, and hence root 2 is an irrational number. That's it. So, very simple problem. Just find out, verify P is an even number and Q is also an even number. Both P and Q will have the same common factor, which contradicts our assumption that root 2 is not rational, it is an irrational number. Okay. Now, let us come to a same type problem. One more problem is there. This is also very important for 3 marks. Prove that 3 plus root 5 is an irrational number. Same type problem. If possible, let us assume 3 plus root 5 be a rational number. So, let 3 plus root 5 is equal to rational number means let us consider P by Q or A by B. Let us consider A by B, a rational number of the form A by P, where A and B are any integers and B is not equal to 0. Now, you just transfer this 3 to right hand side, then root 5 is equal to A by B minus 3. So, A by B is a rational number. 3 can also be written as 3 is also equal to 3 by 1. Again, this is a rational number. So, A by B is a rational number minus 3 by 1 is again a rational number. Rational number minus rational is again a rational number. That means irrational 5 is a rational number. So, here what we will get? Root 5. Root 5, that is irrational root 5 is equal to a rational number. That means a rational number cannot be equal to an irrational number. So, here root 5 cannot be equal to a rational number. It is an irrational number. So, therefore, a rational number cannot be equal to an irrational number. Therefore, our assumption is wrong. That is 3 plus root 5 is a rational number is wrong. Hence, it is not a rational number. Hence, it is an irrational number. 3 plus root 5 is an irrational number. See, very simple concept here. Just assume that 3 plus root 5 is a rational number. Let 3 plus root 5 is equal to P by Q or A by Q. Let us consider A by Q a rational number, where A and B are any integers and B is not equal to 0. So, just keep this root 5 itself and transfer plus 3 to the right hand side. Root 5 is equal to A by B minus 3. So, A by B is a rational number, 3 is also a rational number. Rational minus rational is again a rational number. That is, an irrational number root 5 is equal to a rational number is never possible. A rational number cannot be equal to an irrational number. That means our assumption 3 plus root 5 is a rational number is wrong. Hence, 3 plus root 5 is an irrational number. That's it. That's all regarding this session. Let us meet with the different concept in the next class. Thank you. Thank you very much.